Water, released from clouds in the form of rain, continues to follow the pull of gravity long after it strikes the ground. A considerable part of all precipitation seeps slowly downward through soil and rock to form groundwater. This water reappears in little springs, or bursts out from underground channels like this, or is thrown to great heights by geysers. Groundwater also feeds our wells. Wells are low during dry weather, but following heavy rains, and even before the ground becomes saturated, the water in the well rises since the groundwater level fluctuates with the rainfall. Groundwater is almost universally present near the surface. The upper level of saturation with groundwater is shown in this steep cut. The upper surface of this saturated zone is called the water table. It rises after heavy rains. The water table is considerably below the crests of hills, but it approximates the surface in swamps and marshes, and actually intersects permanent rivers above their beds. Lacking further rainfall, the groundwater, by constant, slow percolation, returns to a more nearly even contour. In this simplified diagram, rain is indicated as falling on porous sandstone which crops out east of the Black Hills. The part that becomes groundwater flows slowly downward and eastward, imprisoned under pressure between impervious beds of shale. When this reservoir is tapped, the groundwater is forced to the surface and surges out in an artesian flow. Artesian wells are common sources of water in the eastern portions of the Great Plains area. Much more commonly, groundwater seeps naturally from fractured or porous rocks, or when the amount of water is sufficient to cause a noticeable flow, it issues as a spring. And here is a hot spring. In such cases, the groundwater probably came in contact with hot rocks deep within the earth. The water issuing from some hot springs dissolves minerals which are carried to the surface and deposited in the form of terraces. Tiny plants that thrive at these high temperatures cause the brilliant color effects of these terraces. These deposits may remain after the springs have ceased their flow. Here they are being quarried. The rock is known as travertine, and it will be used as ornamental wall finish. Some hot springs merely show escaping gases, but others evidence greater agitation. Or the groundwater may be thrown out in the majestic form of a full-fledged geyser. Geysers consist of large underground fissure tubes, as shown by the simplified drawing. This tube fills with water. The geyser owes its activity to the contact of the groundwater with hot rocks far underground. Leading from this region to the surface is a fissure, usually constricted at some points, and with one or more enlarged spaces. Because of the great pressure at the bottom, boiling and formation of steam may actually take place first here, well toward the surface. This expels water from the top, lessens pressure throughout the tube, and then the superheated water at the bottom immediately turns to steam. An eruption results. Let us watch the Daisy Geyser in action. Finally, a period of rest until more steam is generated far below. And now, approximately every hour, winter and summer, its more famous neighbor, Old Faithful. Nearby, in the well-known Norris Basin, there is a veritable family of small but active geysers. Although these hot waters are effective in dissolving minerals, huge underground chambers like these at Carlsbad, New Mexico, were formed by the action of cold groundwater. This sketch of carving caverns from solid limestone shows that the process is both intricate and fascinating. Taking advantage of every fissure or crack, the slightly acid groundwater begins to dissolve limestone. Cavern formation progresses slowly but persistently through centuries on centuries. Groundwater, seeping out from the roof into the cavern air, loses its carbon dioxide and consequently its ability to hold minerals in solution. These minerals, which the groundwater has acquired by dissolving the limestone, are deposited in icicle-like pendants called stalactites. These may be matched by pinnacles called stalagmites, which rise from the floor. In Carlsbad caverns, such formations abound in striking and varied array, roof formations merging with those built up from the floor. We find layers of carbonate rock deposited in fascinating and grotesque forms. Here we see diverging stalactites, which are called staghorns. At some places we find slender stalactites resembling needles. In other passages, confused masses called moss, and in some rooms, sheets resembling draperies. The deposits around this cavern pool are further evidence of the mineral-carrying power of the groundwater. In the Mammoth Cave of Kentucky, streams flow in huge underground channels, some of them extending for several miles. The underground passages have many levels, since they are separated by layers of insoluble rock. When limestone layers have been eroded extensively, the necessary side supports may fall, or the roof itself may disintegrate and collapse. From such cave-ins, there result steep-walled depressions called sinkholes. In some places, these fill with water. When the roof of a cave collapses, a section of more durable or better supported rock may remain to form a natural bridge. Further evidence that groundwater may deposit as well as carry away minerals is found in the petrified forest of Arizona. Here we see giant trees that were buried on an ancient floodplain. Subsequently, their wood fibers were replaced by minerals carried in solution by groundwater. The smallest details of structure are retained, thus giving the appearance of wood, though their original cellulose is now replaced by silica. Likewise, the skeletons of many ancient invertebrate animals were petrified by the replacement action of groundwater, and vertebrate remains, such as this dinosaur skull, also have been replaced through groundwater activity. In somewhat the same manner as cave deposits, small rock cavities or geodes may be partially filled with crystals